So good afternoon everybody. Let us go with the discussion session. Okay, so this is the third live session. I got a couple of queries in the group. Okay, so that I will address first, and then I will try to uh, address your queries the way it is appearing here. Okay, so can you please go to that slide? Yeah, so second one. Yeah, so I received one doubt regarding the calculation of the first element here as shown here. So if 1 1, so if you remember how we calculated, we said that we have to integrate n1 in the given element a1, and then q1 times n1 we have to integrate only over the Neumann edge, okay, or only over the edge where the Neumann boundary condition is specified. So while doing so, when we substituted n1, okay, so we substituted with n1 here x minus y. So here as you can see x minus 1 y times dA integral over a1, and then q1 was 1 in our case, so that's why the second term become, or the second integral become 1 minus y integral from 0 to 1. Alright, so because we are integrating over only this edge, okay, so this is the local edge 1 2 over which we are integrating, so our y varies from 0 to 1 along that edge. Now once we substituted, we have to integrate x over the area and y over that area, so integral x dA, so that is what we are interested in. So let me write, so I have x dA minus we have y dA, okay, and the third term is 1 minus y dy. Alright, integral from 0 to 1. Here it is over the first element a1. This is also over first element a1. Okay. So now when I calculated this x dA, I said that this is the area integral. Okay, first area integral. Now since the x is appearing here, so this term is basically first area integral about y axis. Okay, so that's why I have to find out the, say if this is the centroid here, the centroid is somewhere here, I have to locate the centroid. Okay, so the centroid C, the distance of centroid from the y axis I have to find out, and then I will multiply with the area. So in this case, as you all know, the centroid for this triangle 1 2 3 will be 2 by 3, okay, and then area will be half, that I already mentioned, the area of the triangle is half. And then YDA, similarly when I am integrating YDA, so basically it is nothing but the area integral, okay, about y axis. So I have to find out the distance of the centroid from the y axis, sorry, x axis. Alright, so I have to find out this. So this is the distance of the centroid from the x axis. So what is the distance? In this case it is 1/3. So that's why I substituted that with 1/3 times half. Half is the area. Alright, so I evaluated these two integral, and then this one you can simply do like whatever way we used to integrate. So the first term is basically y, and the second term will be y square by 2, and then if you substitute 0 and 1 you will get half. So that is why the last term was half. Okay, so that is how we get. Okay, so I received one query, so that one I addressed here. Okay, so I will go to the next query where one of you have asked for the calculation of the force term. Okay, possibly Mr. Raphael has asked. Okay, so I'll just address it here. So if you remember, so this was the problem, okay, transient problem that we were solving. The boundary condition is given, so basically at x equal to 0 and at x equal to L, okay, so this is x equal to 0, this is x equal to L, your temperature is always 0. So we have mentioned the Dirichlet boundary, okay, and then the initial condition we have stated that for time t equal to 0, the whole domain the temperature of the whole domain was 0. Alright, so that is what we have mentioned in boundary condition and initial condition respectively. Then we obtained the weak form, okay, following the standard procedure. This we have discussed many times. And then upon that we substituted u and w, okay, following Gallopin principle we substituted with the quadratic basis functions. Okay, here I have derived the quadratic basis functions. This is also available in the solutions of assignment 12. Okay, so so in the right hand side, as you have seen, so this basically represents your fi. All right, so your question is how to evaluate this force term. All right, how to evaluate this force term. So as you can see here, for this particular problem it is very easy, because I have said that the heat generation term is G equal to 1, so this is constant. Alright, and phi I we have already defined. Alright, n1, n2, n3 we have defined. In this case we have taken only one element and we have taken degree p equal to 2. So that's why we have p plus 1. We have 3 basis functions. Okay, we are choosing quadratic step functions. So we will substitute the corresponding phi I and we will integrate from 0 to L. So that is the first term. And if you look at the second term, so for this problem the second term is 0, because at x equal to 0 and at x equal to L, at both the ends temperature is specified. Alright, so and we said that in a given problem, when your primary variable is defined at the boundary, there your weight function, okay, has to be 0. Okay, so in that way this term is 0 for the problem in hand. Okay, but in practical case there will be, obviously there will be certain non-zero terms. Now if I concentrate on only on fi, okay, so now let us go ahead and see how we need to calculate fi for the problem in hand. So let me just tell you, we have so while taking this set of ordinary differential equations and writing in terms of linear algebraic equations, we took help of this time marching scheme, and we said that for this scheme, for this problem we will choose mu equal to half. Alright, so now when this is substituted, okay, we get the set of discrete equation, and that turns out to be like this. Alright, this is also there in the assignment solution. Okay, so now you just look at it. The right hand side, if you see this term, okay, it has two force term, one at t equal to tn, so fn basically corresponds to time tn, and fn plus 1 corresponds to time tn plus 1. Alright, time tn plus 1. So we have to evaluate this force term, but as I said, fi in this case is g times, you can say ni dx, okay, 0 to L, because the second term is 0, so I am just putting it as 0. Okay, but in this case g is 1, so in one way fi is going to be constant for our problem. Alright, so for our problem your fn and fn plus 1 is going to be same. Alright, that is I think the question asked by Raphael. So for our problem fn and fn plus 1 is constant, but suppose you have a domain, okay, and you have a element, or you have one element inside the domain which is basically constantly getting heated up. Okay, and in that case your g will be a function of time t and x. So in that case you have a term t here. Alright, so in that case your f will be function of time instant tn. So when you will be integrating over the domain, okay, you have to take the corresponding value of g, okay, by substituting in this function. So you will be given a function gt comma x. Okay, so if I want to calculate fi at time tn, so I have to evaluate this function at time tn and at the Gauss points, okay, xg. So I have to evaluate this function at a particular time instant. So in that case your fn and fn plus 1 will not be equal. Alright, but for this problem your fn and fn plus 1 is same. So you are heating the domain with a constant heat source, okay, and initially the temperature was 0 everywhere, and suddenly you have switched on one heating element, so obviously your temperature is going to change with time. Alright, now what we have done, since this term is constant, now what we have asked for is this delta t term, okay, time step. So that time step we are asking you to change from 0.1 to 0.25 to 0.5. Okay, for these three time steps we asked you to solve the problem and check the value of the temperature at the midpoint of the domain. Okay, why? Because this is just to show you that the choice of time step actually decides your approximate solution. Okay, so if you remember, in case of steady problem we said that when you get a solution at the end of your end of the running of the code, then you are getting basically an approximate solution, and you should always check for mesh convergence. That is, you need to increase the number of elements, or you should refine the domain by more number of elements, and you should check whether you are getting a constant or not changing value of the solution. Okay, your solution should not depend on the mesh. Okay, till that point you should continuously increase your mesh size, the number of elements. Alright, but in this kind of problem, unsteady problems, the mesh convergence study is important. Parallelly, your time step is also important. So as I said, you cannot take a large time step, then in that case your solution may be unstable, and because that depends on the numerical process or procedure that you have adopted, and the solution can be inaccurate. Okay, and if you take too small time step, then the code will take long time. Okay, so it will take lot of time to give you the result. So that's why how the solution changes with time step. Okay, in order to convince you that solution do change with time step, we have actually taken this problem. Okay, so if you, as you have seen that as you change the time step, as you take smaller and smaller time step, your solution actually converge. All right, so that time convergence study in addition to the mesh convergence study is required for unsteady problems. So that was the purpose of the problem. Alright, so I think I have addressed your issue. Then another query that I have received is regarding the regarding this particular function. Okay, I showed you the code for solving steady state heat conduction problem. There actually this code I didn't show, this piece of code, because my purpose was to illustrate the procedure. Okay, so anyway, so let me just explain it to you. So here what we have done in this piece of code is, for degree p equal to 1, if I take a quadrilateral element for degree p equal to 1, then as you know, for steady state heat conduction problem we have 1 DOF per node, and for this element we have one node. Okay, and we have 4 nodes, and in each node, as you can see, these nodes are actually coinciding in the vertices of the quadrilateral. So we have a mesh. Okay, and it is everywhere. So in each element, if we remember, I have actually numbered the nodes. So this we said as local numbering. So in this case I am just numbering as 1, 2, 3 and 4. Alright, and this numbering we have done in such a way that we always start from the lower bottom left bottom corner of a given element. So this is the local number, this is related to that particular element. So now what we have done in this variable local nodes on edge, row wise I have basically arranged the local numbers. Alright, so I said that in edge 1, so this is edge 1, the local node number are 1 and 2. Edge number 2, the local nodes are 2 and 3, so that is there in the second row. And edge 3, the local nodes are 3 and 4. Alright, and edge 4, the local nodes are 4 and 1. So that is what has been arranged here. Alright, Now if you move to degree p equal to 2, let me just show you. Okay, if you move to degree p equal to 2, so you have 9 nodes. Okay, Lagrange element if you take for p equal to 2, so in that case numbering is 1 2 3 4 5 6 7 8 and 9. Alright, now if I age wise, if I just note down the numbers, now in age 1 the nodes are 1 2 and 3, so that is there in the first row. Okay, and if age 2 the local nodes are 3 4 and 5, so that's why that is what is appearing in the second row. Similarly 5 6 7 appearing in the third row, and fourth row comprises of 7 8 and 1. 9 is not appearing because 9 is an internal node. Okay, here we are noting down only the nodes on the edges, so that's why I have given this number or name local nodes on edge. Okay, so depending on degree p we actually have defined these numbers. And interestingly, if you see the first column of these matrices, okay, they basically refer the corner nodes. So if you look at p equal to 1, the first column 1 2 3 4, that refers the corner nodes. Similarly for p equal to 2, the first column refers to the corner nodes 1 3 5 and 7. Okay, and how these are used, as you can see here, in order to calculate the Jacobian we need the coordinates of the corner nodes. Okay, because we are using linear mapping, so that's why these local nodes on edge, the first column we are collecting, so that gives us the local node numbers of a given element, and that we are using to find out the corresponding global node numbers from the connectivity matrix. And from that global node number we are calculating the coordinates of the corner nodes, which we will be using to calculate the Jacobian. Alright, similarly when we integrated the Neumann boundary, okay, we need the length of the element h, okay, because that appears as h by 2 as Jacobian in the during numerical integration. So in that case also we are using the same variable, which basically helps us to find out the coordinates of the corner nodes. Okay, once we know the coordinate we can find out the length of the edge. Okay, so that is how it has been used in the code. Okay, so final query that I have received is how these boundary conditions are to be dealt with. So in this problem, as you can see, this is a beam element. Okay, this undergoes bending, and as you can see, at these two ends, at x equal to, say if I give this as x coordinate and this as y axis, alright, so if you can see at point B, okay, it is pinned, so it means the axial displacement of point B. So if I say u is the axial displacement, okay, or you can say u is the displacement along x axis, u at B, okay, is 0 because it is pinned, and v, the transverse displacement of point B, is also 0, that is pinned. But if you look at point A, okay, point A is on a you can say roller support. It can move along x axis freely. Okay, it can move along x axis, but it cannot move in the y direction. So in that case, is basically v at A is basically 0. It cannot move in the transverse direction. Alright, so u and v are basically the displacement along x and y direction. Alright, so now what are the boundary conditions? So in this case we have taken Bernoulli beam problem, so we are only interested in the transverse deflection and the slope. So if you look at point B, okay, your transverse displacement is 0, so vb is equal to 0, or you can say y at b equal to 0, but your slope is not restricted, so it can freely rotate about that point because it's a pin joint. So in that case the moment, okay, is 0. Similarly here at point A, your transverse displacement is equal to 0, okay, and your moment at this point is also 0, but your axial displacement is not restricted. So this is the piece of boundary condition that you have to use and find out the eigenvalues. Alright, So hope this helps. So with this I will put an end to my presentation, and I will just try to address some of your issues as it appearing in the YouTube. Can you please change that live session, live part? Okay. As far as I understood, for natural du dx would be given for us. Yeah. Yeah. So I have addressed your issue. So okay, let me wait for some time because I do not have anything. Uh, yeah. So when yeah. So yes. So if I have understood, is basically what you want to mean is uh, in some problem I have used the matrix notation. Okay, you said that n so n times alpha. Okay, in order to describe the displacement, and in some other cases I have used as alpha I n I. Okay, so that is what, so these two are basically equivalent. Okay, if you can find out the integral in terms of one notation, okay, you can find out in terms of the other one also. Okay, so there is no difference between them. So particularly when we are looking for the right hand side, so typically say suppose if I take the steady state heat conduction problem, the right hand side Fi, uh, we have g, which can be a function of x, and so in this case it's a function of x, and then we have typically ni dx. Okay, say if I take one dimensional problem, so as you can see, if I substitute one n, okay, and I will get the corresponding value of fi. Okay, so and then when we did it in terms of the matrices, it is basically equivalent. You do it by yourself, it will not be that much, because in that case this matrix is basically a row vector. Okay, so if I take say n1, n2, n3, okay, and so this is a row vector times you have alpha 1, alpha 2, and alpha 3. So that basically you represents your u. All right, so this times this is same as alpha I in I. Okay, so you can substitute any one of them. Okay, and then in that case you have to integrate element by element. Okay, so in that way you will get the same thing. All right, so if you have any more doubt, you just put that question in the group. I will try to address it with an example. Okay, fine. There is a lag, no? There is a lag between whatever and appearing in that. We have the same question. Yeah, so I want to address. Yeah, so Rafael, coming to the exam, actually you can expect similar problems that is appearing in the assignments. Okay, we'll give a complete question. Okay, and we'll tell you the steps. Basically, the questions will be the steps. Okay, so if you try to address each of the questions one by one, you will be able to solve the problem completely. So that is how the problems are defined. So you can say if you can solve the assignment problem, you will be able to address most of the questions appearing in the exam. Okay, and the pattern is same as that of the assignments. Only one student is asking. Only one student is asking. Is it over or should we continue? Fine. I am fine. I am fine. Yeah, so coming to your previous doubt in deriving the stiffness entries and other matrices is basically same as whatever we did in this course. So basically you first have to derive the weak form, and once you derive the weak form you just substitute the primary variable and the weight function in terms of the basis functions. Okay, the linear combination of the basis functions. So that is how I have derived all the problems. Okay, starting from steady state heat conduction to the transient problem, and then eigenvalue problems. All the steps were same as the previous problems. Okay, one dimensional problem. So I think it is not different. And coming to your last question, that regarding scientific research problem, you can always mail me in my email ID. So that is on my web page. So you can always send me an email, and we can always discuss. Then coming to another question uh, by Gaurav, do we have to access to MATLAB in exam? No, you don't need MATLAB basically. Okay, we have ensured that without MATLAB you will be able to derive all the entries. Okay, so all the calculations it is possible to derive by manually. So that is what we have ensured in the exam. Okay, you don't need MATLAB. Uh, can you explain in short to calculate M matrix for transient problem? Yeah, Dilip, I think I have explained it in detail in the literature. Please go through it. Okay, so as I said, Mij in that case, I think it appears as uh, if you look at the mass term, so probably it contains some. So in say elasticity problem, it will contain density, and then you will be having some shape functions Nij. Okay, and then or you can say it has to be over domain. So simply you have to integrate this rho Nij d omega. Okay, so this I am talking about in terms of index notation, and since we have introduced index notation in our lectures, okay, if you go to the previous lectures by Professor Arup Nandi, so we have actually introduced the index notation. So either you can stick to index notation or you can use matrix notation, and you will be able to calculate the mass matrix. Okay, I think in one of the problems we asked for this. You need to, because the unsteady problem you need to calculate the mass matrix. Okay, you can actually find out that problem and you can solve it again. All right, so that will help you. Yeah, so you, if you have any more query, you can put it here. Okay. Yeah, thank you, Raphael. So our course helped you out, so it's good to know. Okay, we are glad to know that this course helped you. Okay, thank you. All right. Okay, so if you have any more query, put it here. Otherwise, I will leave in 1 minute. Okay, thank you all. And you study those materials, go through the lectures repeatedly. If you have any more doubt, you can send a query in the group or you can send me personal mails also. Okay, thank you.